Alright, welcome to this lesson on how do we find loci. Alright, so let's go on to the preliminary activity, but before that, let me just introduce you to your friend, the compass, okay? The compass is an instrument used to make circles, okay? So, there are different ways of using the compass, and I'm going to show you right now. Let me see if I have... Okay, the compass is used to make circles. So, I'm going to make circles. Let me do it on the other side. So, the most effective way for me to create a circle is to grab the compass, right? Now, exercise all the pressure on this leg, leaving, leeway to this other leg to move about, to move around. All right? Now, if I move the compass like this, I think I will only get halfway. I won't be able to go around. So the best way for me to do, okay, if you have space, make sure your desk is clean. Just put the compass here. And remember, exercising all the pressure here on this leg, not on this one. So then move the paper around. Okay, without moving the compass, move the paper around. Actually, I can move the compass if I wanted to, okay? And I still keep the other leg on the same spot. See that? So you continue, okay? Move around, you move the paper. And guess what? You create your circle. There you go. Okay, that's one way of doing it. Moving the paper around. The other way of doing it, okay, is basically grabbing the compass from here. And although this is in the middle, you could still exercise all the pressure here. And just a little bit on this other leg. Look. Now, if you move forward, you slant it forwards. If you move backwards, you slant it backwards. As simple as that. See that? This is not a contest of how dark you can make your circle. Trust me, I can see it even if the circle is only drawn like this. See how light this is? It doesn't matter. Maybe you cannot see it right now, but I can see it. It's right there. So again, it's not a contest of how dark you make your construction. Alright then, so let's move on to the lesson. Okay, let me do a close-up in here. Very good. So the first exercise, is to draw the points that are 1 centimeter from the given point, right here. Alright, so take 1 minute to figure out, and look, you need to draw conclusions and write what your conclusion is. So let's wait 1 minute. I'm going to pause the video. And whoever gets it, then I'm going to give you 1 point. So this is how you do it. So this is 14, right? So 1 centimeter will be going on to 15. Or if you don't want me to measure like that, then easy. I'll go from 0 to 1. Okay? Now, some of you are making the mistake of going another centimeter from the other point. No, it's 1 centimeter from the given point. So from this given point, you're gonna draw another point that is 1 centimeter away. Then another one that is 1 centimeter away. As many as possible, okay? And that will help you draw your conclusion. Just 1 centimeter. It doesn't have to start from 0, but you have to know what 1 centimeter is. Alright, this should be enough for you to draw your conclusion. Okay, if you already did, I already gave you the points. If not, then your conclusion is that when I try to draw all the points that are 1 centimeter away from the fixed point, I come up with a circle. Okay, so what is it that you were supposed to write? Well, all the points that are 1 centimeter away from the given point, okay, will form a circle. So this is the way you're supposed to write it. The locus of points equidistant to a fixed point is a circle. Now, do you have to memorize this? Hell yeah, you better memorize this. And you know what? Let me just do this early in the video. Oh, look at this. Okay, good. Now it's good. Okay then, so first question for another point. What does the word locus mean? Is the set of all points that satisfy a certain condition. All right? All right, so if you answer, you already got your point. Now, please raise your hand if you want to answer, okay? I will ask each and every one of you. Now, for another point, what does the word equidistant mean? That's for another point, okay? 5 seconds. The word equidistant means the same distance. So what you want to do right now is you want to go over here and write equidistant means the same distance right on this blank space. Okay? Good. Now let us go on to the second problem here. All right. So pretend that these parallel lines are 2 centimeters of distance. Now you're going to draw all the points that are equidistant, in other words, the same distance, okay, from the given parallel lines. So, what do you think? Take 1 minute to do it.
You know what you have to do? You have to create the perfect time and the perfect opportunity and the perfect situation.
Wow, they are almost 2 centimeters away. Okay. So this is like halfway the distance, okay? So there's 1 centimeter from here to here and 1 centimeter from here to here. So that means this point is at the same distance from these two lines, okay? Okay then. So now let's connect these points, okay? Now I could have done infinite many points, but I just decided to do this couple of points. Look, you go to 1 point here, 1 point here, 1 point here, 1 point here, 1 point here. Doesn't matter. But the locus of points, once you connect all those points, guess what? You end up with a line in the middle. And now, for your conclusion, you're gonna write the locus, okay, the locus of points, the locus of points equidistant, just like in the previous problem, equidistant to a pair of parallel lines is a line in between or in the middle, whichever way you want to write it. All right, see, that wasn't that bad. I'll let you copy. All right, let's move on. Okay, cool then. Now remember something, for these you really need to use your common sense. So now this problem says draw the points that are 1 centimeter from the given line, okay, as many as you can, and from that make your conclusion. What do you notice? All right then, so take 1 minute, and whoever gets it, raise your hand, okay, before I finish the problem. Raise your hand, I'll go check, and I'll give you 1 point. And that's how it works. That's how you're gonna get some free points. right, so 1 centimeter is right here, right here, right here, right here. Oh, I see how it goes. Okay, so I already know what's gonna happen. So it's gonna be a line right here. Now, most of you are gonna call me and say, "Oh, Becker, I got it." But you know what? No, you don't got it. You know why? Because there's 1 centimeter from this line. Guess what? This right here, it's also 1 centimeter from this line. This point right here is also 1 centimeter from this line. This point right here is 1 centimeter from this line. And when I connect this, I get another line. Oh, Becker, you OD, you nice, you besting, son. Okay. So, let's see now. Conclusions. Wait, hold on a second. But Becker, this is the opposite of this problem right here. Right. Exactly. You have parallel lines here and you had a line in the middle. Well, here, I could say the same thing. What is the locus of points equidistant from this line or to this line? A line on top and a line in the bottom. In other words, a pair of parallel lines. So then you're going to write the locus of points equidistant to a pair of parallel lines. I'm sorry. The locus of points equidistant to a given line, okay, a given line is a pair of parallel lines. So take 1 minute to write that down. And if you don't know or you don't remember what to write, just look over here. Just look at the other example. The locus of points equidistant to a given line is a pair of parallel lines. Your common sense should dictate that. All right, cool. Let's move on. All right, here it says draw the points that are equidistant, okay, from these 2 points. So I'm going to tell you right now, since you don't know this, the locus of points equidistant to 2 given points, okay, is the perpendicular bisector. So, and how do I construct the perpendicular bisector? Easy. Open your compass with this little wheel right here, okay? Let me just zoom out just so you could see it better, okay? You see, this is the adjustable wheel. Ah, nice. Open wide, close narrow, open. So you're gonna open this compass to more than halfway the distance between the points. And please don't ask me, Becker, is this more than halfway? Is this more than halfway? No, you should know. If you must use the ruler and say, okay, what is more than halfway? Okay, this is the middle, this is... No, you don't even need to measure that. Just go more than halfway. Watch this. Is this more than halfway? Hell yeah, look. This space is wider than this space. So that means that I travel a distance more than halfway. Even if I was around here. So what you're going to do is you're going to create 2 semicircles. Now, why do I say semicircles? Okay, the most efficient way would be 2 circles, but no. So you're gonna create 1 semicircle right here without moving the width of the compass, okay? You're gonna go to the other point. You know what? Let me call this point A and this point B. Okay, so you understand. So you're gonna go to point B, okay? You're gonna go to point B and you're gonna draw another semicircle. See that? Like 2 intersecting arcs right there. And now what you're going to do is you're going to connect the points where the 2 semicircles or 2 arcs or 2 circles, whatever you want to call it, where they intersect. So you're going to connect it. Nice. That, my friends, is called your perpendicular bisector. Now, perpendicular bisector to what? Okay, let's say it wasn't just the 2 points. It was actually a segment that connected the 2 points. So this line right here is perpendicular, meaning 90 degrees. Okay, you should be doing this. and it's also at the midpoint. Believe it or not, I'm not using the ruler. I did not use the ruler to determine what the midpoint was. I used the compass to create the circle, the semicircles, okay, the intersection. And basically, none of your measures are going to be the same. Like your arcs are going to be, maybe one of your arcs is right here, the other one goes through this point or whatever. But one thing that is true is that this will always be the midpoint, and all of you are going to find it to be the same measure from here. I'm telling you right now, there's gonna be 1, 2 and something centimeters, and look at this, 1, 2 and something centimeters from this point, the midpoint. All right, then let us move on to the next problem. Oh wow, draw the points that are equidistant. So what you're gonna write is the locus, okay, of points equidistant, just like this one, the locus of points equidistant to 2 points is the, okay, perpendicular, and this is how you denote perpendicularity, okay, an upside down T, is the perpendicular bisector, okay, good. Now remember, you gotta write the whole thing, the locus of points equidistant, because when I check your binders, I want to see this already there. All right, then let's move on. All right, just in case, right now for 2 points, no, for 1 point, I'm sorry. What is locus? 5 seconds. Raise your hand. Oh, time is up. Okay. Once again, if you got it, you got the points. If not, I'm gonna tell you, locus is a set of points that satisfies certain conditions. All right, I got you again, right? Okay, then. So here it says, draw the points that are equidistant from these 2 intersecting lines. Sure, why not? These are 2 intersecting lines. 2 intersecting lines form 4 angles. Okay, so basically what you're gonna do is you are going to trace, you're gonna divide the angles into half, okay, and that is called the angle bisector. Angle and bisector means that it divides it in half, just like perpendicular bisector means 90 degrees and midpoint. So just an estimate, okay, don't be calling me saying, Becker, is this right? No, just do an estimate, okay, see that? Now the angles go, look at this angle moves and goes on because he has the arrowhead. Same thing here. So that means that when I do the division, I also have to put arrowheads. Ah, nice. And here you do the same thing. You chop this angle in half. Okay? I'm just doing an estimate, so it's not like, oh yeah, you're off by like 1 millimeter. And do the lines have to be like vertical and horizontal? No. Look. These lines are not vertical and horizontal. These are the originals, and this is the locus. Okay? Once again, locus is a set of points that satisfies certain condition. Alright? And look at this. AB, which is this, is perpendicular, that's how you read it, to CD. Ah, Baka, you're nice. Alright then. So let us recap on what we have seen or learned so far. So the locus of points equidistant to a fixed point is a circle. The locus of points equidistant to a pair of parallel lines is a line in the middle. The locus of points equidistant to a line is a pair of parallel lines, a line on top and a line in the bottom. The locus of points equidistant to 2 points is the perpendicular bisector. Okay? The locus of points equidistant to a pair of intersecting lines is nothing more than another pair of intersecting lines, which in reality are the angle bisectors. Okay? 4 angle bisectors. 1, 2, 3, 4. Same thing here. Okay, then let's move on to this problem right here. So the treasure. I was gonna make you write this down and do it as a task, but no. All right, so it says a treasure is buried in your backyard. The picture shows how your backyard which contains a stump. I'm assuming that this is the stump, okay? Because I have no idea, okay? Because watch this, which contains a stump, a TP. I'm assuming that this is the TP, or either this is the TP. Now this is the stump, this is the TP, okay? And a tree. The TP is 8 feet from the stump. The TP is 8 feet from the stump, okay? And 18 feet from the tree. Ah, nice. So now I know this is the TP because it's 8 from here and 16 and 18 from here. All right then. Now the treasure is equidistant from the TP and the tree. So the treasure is somewhere in between, okay? It has the same distance from here than from here, okay? But it's also 6 feet from the stump, right here. 6 feet. Locate all possible points for the buried treasure. All right, guys. For this, for visual purposes, we have to understand something. When we look at stars, we don't really look at the planets or whatever their shape. We know that some of them are round, some of them are maybe not so round, but sometimes it's like we look at stars and we look at dots, okay, little dots in space. So that's exactly the way we should look at this. Let's pretend that these are nothing more than points in geometry. All right, so let's see now. It's equidistant from the TP and the tree. So this is one point and this is another. Okay, what is the set of points equidistant from 2 points? The perpendicular bisector. Okay, we just did that. So that's exactly what I'm going to construct. So I'm going to put, okay, I'm going to label the points. I'm going to call this point T for tree. I'm going to call this, gosh, but then this is a TP. Point P for TP. And this is point S. Look at where point S starts. Starts right here. So this is point S. Okay. So equidistant from T and from P? Sure. Start right here. Open more than halfway. I believe that this is already more than halfway. If I put my fingers here and my fingers here, this is a greater distance. So that's more than half. So I'm going to go ahead and draw a semicircle. Remember, the easiest way to use the compass is just to move your paper around. See that? And now, without changing the length of the compass, we go to the other side. And we'll do the same thing. Nice, like a crayfish, if you ever seen one. Or the antennas of a lobster. So now I am going to connect these points. Baby, you're nice. Okay, so this is what's equidistant from these 2 points. But it's also saying that it is 6 feet from the stump. The stump, remember how are we visualizing these things as points? So 6 feet from a point. Well, isn't that the same as the question I asked you about 1 centimeter from this point? So for 1 point, answer me this. What is the locus of points equidistant to a fixed point? What shape does it have? All right, hopefully you're raising your hands. All right, cool then. So from here to here is 8 feet. I need 6 feet. Okay, in reality, this is not feet. This is like maybe centimeters, whatever, but we're just doing an estimate. So I'm going to say that 6 feet is around here. Would you believe me if I tell you that 6 feet is around here? It's more than half. Okay, so since the locus of points is a circle, I am going to accommodate my paper to suit my needs, okay? And I am going to place my compass around here, okay? Just an estimate, okay? Or actually, you know what? It doesn't intersect here, so I'm gonna make it, you know what? Forget it. Just do it closer, as close as possible. This is not gonna be the point. It's too close. Okay, pretend that is around here, yeah. Let me see. Yeah, around here. Okay. So now I'm going to do my circle. Yeah, I'm not following my advice, so let me move the paper like that. Okay, cool. So now, okay, so now all I have to do is label all the points of intersection. Okay, if this line continues this way, which it didn't, okay, you use a ruler, I'm not gonna use a ruler, then the points of intersection are right here and right here. Now, it's amazing. It says, locate all possible points for the treasure. Well, this treasure is equidistant. Okay, any point in here is equidistant from these 2 points. So, anywhere around here. And anywhere around here, okay, is 6 feet away from the stump. So, the loci, because it's 2 locuses, okay, but we don't say locuses, we say loci. That means two or more locus, okay? Wherever they intersect, that will be your solution. So in this case, this treasure is equidistant, okay? It intersects the circle, which is 6 feet from here, and it's also equidistant from these 2, the TP and the tree. This point is also equidistant from these 2 points, and is 6 feet from this one. So the treasure could be here or here, okay? So we have actually reduced all possibilities. Now, of course, if you didn't get it right, don't worry, you have the diagram right here, okay? See that? Of course, this is computerized, so I guess it's better than mine. All right then, so it says explain your reasoning. What do the points of intersection represent? Well, I just told you. The points of intersection represent the intersection, okay, of the locus or locuses, or the intersection of the loci, meaning that each of the intersection point is equidistant from the TP and the tree, and also 6 feet from the stump. All right, let's move on. Okie dokie. So let's start with the real thing. Gosh, too big. Too small, too big. BEKER, what you getting yourself into? Oh, got it. Okay. Good. Why did the chicken cross the road? Who cares? All right. In the diagram below, car A is parked 7 miles from car B. All right. So the first thing you need to know is that the distance from here to here is 7 miles. Okay. Sketch the points that are 4 miles from car A and sketch the points that are 4 miles from car B. All right. 4 miles. What does 4 miles represent? Well, I could tell you. Okay, if this is 7 feet, right? Then somewhere around here is like 3.5. I'm just saying, I'm just saying. This 3.5. So a little more right here should be like 4, right? Right? Okay, so that's exactly what I'm gonna do. And anyway, just remember, it says sketch the points that are 4 miles from car B and from 4 miles from car A. Label with an X all points that satisfied. Okay, so 4 miles. This is more than a half, right? So that means that it should be 4 miles. So watch this. 4 miles from car A, all over, okay? Remember, I'm doing this because I'm nice, but you could just move the paper, okay? Please do me that favor so you don't make any mistakes and your circle comes out to be perfect. And not only that, you want a perfect circle? Then do not exercise pressure here. All the pressure should be on this leg. Okay, look. See that? How fast I move it? Oh my God, you're seeing 2 compasses. No, not really. Remember, it's not a contest of how dark it is. It's about how perfect. So it could be a slide. The other one, I'm gonna do it lighter. Anyway, so this is 4 miles to my calculation. Guess what? Without changing the length of the compass, that should also be 4 miles from car B. Okay? Now, if I was just doing this, then that will be the perpendicular bisector. But they are asking me for 4 miles from each car, and I know that the locus of points to a fixed point is a circle. So I'm gonna move the paper. You see, I'm not even stressing, I'm not struggling with this because I'm not pressing hard. Please don't do it, because if you do it, then guess what? You're gonna ruin this. Trust me, you are. And if you do, I'm gonna charge you like 25 cents. Alright, no, I'm just kidding. I will charge you more than that. Alright, so label with an X all the points that satisfy both conditions. What were the conditions? 4 miles from car A, and at the same time 4 miles from car B. All this is 4 miles from car A. All this is 4 miles from car B. But only this point right here belongs to both circles. So it's 4 miles from here and 4 miles from here. Guess what? This other point, this other X, sorry, mine are not X's, yours should be X's, is equidistant from both points. 4 miles. Alright? Good job. Alright, from now on, what we're gonna do is we're gonna represent locus with dashed lines, so we know the difference between the original and that. Alright, so a man wants to place a new bird bath. Bird bath. The hell, they're gonna do like a tiling and like a shower or something. I don't know, who cares? A new bird bath in his yard, so that is 30 feet from a fence. This is the fence. A fence is a line. So look back in your notes and tell me what the locus, what the points equidistant to a line forms. 5 seconds. 1, 2, 3, 4, 5. Okay, time is up. So the points, okay, equidistant, all the points equidistant to a line is nothing more than another pair of parallel lines. A pair of parallel lines. So that's exactly what I'm gonna do. So it says it has to be 30 feet from the fence. So all the points that are 30 feet from the fence. From here to here is 35. So my assumption is gonna be that around here is 30. Do you see it? Do you understand what I'm saying? So right here should be 30. So that's exactly what I'm gonna do. Look, I said that I want you to represent the locus as dashed lines. So that's it. Guess what? It's a pair of parallel lines, so the other line should be around here. Now, fun fact is that I don't need this side. They might ask you to do it, or you might want to do it, but all I need is this side right here. I'm working on this side, but anyway, this is sometimes necessary. All right, and also 10 feet from the light pole P. Guess what the light pole is? The light pole is a point. So 10 feet from a point. Okay, I'm gonna give you 1 point and you got 5 seconds. What is the locus of points equidistant to a point, a fixed point? What does it form? A line, a circle? Raise your hand if you want me to give you the points. Correct, it's a circle. So I'm gonna grab the compass again, okay? Exercise the pressure here. Now it's 10 feet from this point. Well, from here to here, tell me how much distance there is. Yes, there are 5 feet, because from here to here there are 30, and from here to here there are 35, so this is 5. So 10 should look somewhere like around here. Make sense to you? OD. Alright, so that's exactly where I'm gonna place my compass. Okay, right here. And look, do it light. Okay? Light. All the pressure is exercised on this leg, not on the other one. Look, if I can do it, you can do it. You can do it. You can do it. All right. Now, BEKER, you said to do the locus of points as a dashed line. Yeah, but how am I going to do dash? Well, actually, I could if I wanted to. But the circle, come on. All right, so where do the loci intersect? Right here and right here. That means that right here is 10 feet from the pole and is also 30 feet from the fence. And the same thing goes here. All right. So how many possible points are for the bird bath? There are 2 possible points. Oh, BEKER, you're nice. All right. Next. 2 lines AB and CRD are parallel and 10 inches apart. So these are 10 inches apart. All right, fine. Sketch the locus of all points that are equidistant from AB and CRD in 7 inches from point R. Okay, so they want me to sketch all the points that are equidistant from 2 parallel lines. So I'm going to give you 5 seconds and tell me what the locus of points to 2 parallel lines is. 5 seconds. And you got to raise your hand. All right, time is up. Yes, you're right. It's a line in the middle. Am I going to calculate? Nah, I more or less have an idea of what it is. No, it didn't come out right. So I'm going to make it around here, okay? That should be 5 feet. If you want to, you could use the ruler. I mean, I don't care. Now, if I really wanted to get the line in the middle, I could have just drawn the perpendicular bisector right here. I could have gone like, okay, let me go, and let me go like this from here to side. You know what? Forget it. I'm not going to start with this because it's going to take me too long. So I got this. This is the line in the middle. What else? They want it to be 7 inches from point R. Point R. What is the locus of points to a fixed point? It's a circle. So from here to here is how much distance? Raise your hand if you know. Okay. Yeah, 5. So from here to here is 5. So 7 should look like from here to like around here. Yeah, right? Okay, so let's do that. So I'm going to do a circle with center at R. And I'm going to do the wheel. I'm going to narrow it all the way until it fits the description right here. Oh, see that? Okay, so now I just draw my circle. You know what? I'm going to move the paper. You see, I'm not pressing too hard. All the pressure goes on this point. On this leg, sorry. All right, so now it says what? Label will annex all the points that satisfy? Sure. All right, that's it. Oh, you know what? I also made a mistake. Not a mistake, but this was supposed to be a dash line. Gosh, Becker, you keep on messing up, okay? I will use proper English. Proper English. Okay. The length of AB is 3 inches. This is 3 inches. On the diagram below, sketch the points that are equidistant from A and B. From A and B? Sure. Equidistant, you know, what is the locus of points equidistant to 2 points? The perpendicular. I'm not going to say it. I'll give you 1 point. Raise your hand. Time is up. Okay. It's the perpendicular bisector. And how do I draw it? I open the compass to more than halfway, okay, the length of the segment or the length of the 2 points. I could have done it here if I want to. You know what? Let me do it over here. This is OD mad long, right? More than halfway OD. Meaning what? That your measures don't have to be the same. So you sketch 2 arcs, okay? 2 arcs. That's how you draw the perpendicular bisector, 2 arcs. Or you could do 2 circles. Or you could just draw 1 arc and then with the other one just do the intersection points. See that? So now I'm gonna draw my line right here. Damn, that was mad long. Yeah, I exaggerated it. Okay, so this is the perpendicular bisector. This is all the points that are equidistant from A and B. Now let's see the other part of the question. And sketch the points that are 2 inches from point A. 2 inches from point A. So just 2 inches from point A? Fine. Look. I know that the distance from here to here is what? You got 3 seconds to say it. Oh, you didn't get the 1 point. Okay. The distance from A and B to B is 3 inches. So from here to here, since this is the perpendicular bisector, is 1.5. Because that's the midpoint. So 2 should be around here. Got it? So 2 inches from point A? Sure. What is the locus of points equidistant to a point, to a fixed point? A. Yeah, now you got it. It doesn't matter if it goes over to the next thingy. All right, so I got it. I'm nice. It's a circle. All right, guys. Now it says label with an X all points that satisfy both conditions, meaning at the same time. Equidistant from here to here, and also 2 inches. Well, one is right here, and the other one is right here. That's it. That solves the problem. Cool then. All right, finish up. All right, cool then. Let's move on to the next problem. All right, so let's look at the problem. It says a city is planning to build a new park. The park must be equidistant from school A at 3,3 and school B at 3,-5. So the first thing that you're gonna do right now, right ahead, right away, is to plot the points. 3,3 and 3,-5. 3,1, 2, 3, okay, and 3,1, 2, 3, 4, -5 right here. Okay, school A, school B. Perfect. And now it has to be equidistant. So what is the point? What is the locus of points equidistant from 2 points? The perpendicular bisector. But then here you don't have to measure anything because you already have the little units. So let's figure out the distance from A to B. 8. So half of 8 is 4. So 1, 2, 3, 4. So the perpendicular bisector is going to go through this point, which is the midpoint. Now, of course, you're not used to seeing the 2 points like this. You're used to seeing the 2 points like this. So that's how I'm going to do it. All right, so it's going to be right here. Now that's going to be my locus, okay? So that means that it's going to be dashed. I just, for visual purposes. I like it when you call me Big Popo. Damn, Spanish accent. Okay. All right. I'm doing a good job. So this is the perpendicular bisector between these 2 points. Okay, what else does the problem say? The park must be exactly 5 miles from the center of town, which is located, okay, at the origin on the coordinate graph. Each unit on the graph represents 1 mile. Yes. On the set of axes below, sketch the compound loci. You see that? Compound loci. That means more than one locus. And label with X all possible locations for the new park. Sure. If it's located 5 miles from the center, and the center is located at the origin, this is the origin. 0, 0. Okay, 0, 0 is the point. So 5 miles from there? Sure. Take the compass, okay? Take the compass and go put the middle part on the origin, the center of the town, and the other one open it to 5. Now, funny thing is that you might think that, oh yeah, but it's not gonna come out exactly. Well, watch this. The pressure on this leg, this one must be like, oh, loose. Okay. Now watch me. Okay. Now look at your circle. 5, 5, 5. Nice. Now it says label with an X all possible locations for the new park. Sure. Where do the compound loci intersect? Right here. Right here. So these are the 2 possible locations. All right. Let's move on to the next problemo. Now, guys, if you already get the hang of this and you already know what's going on, then please go ahead, go faster than I am, by all means. All right, let's do this. So on the set of axes below, sketch the points that are 5 units from the origin and sketch the points that are 2 units from the line y = 3. Okay, 5 units from the origin, I already know what's up. Everybody knows, we just did it. So 5 units from the origin, put the compass here at the center, go 5 units here, okay, and you sketch your circle. Okay, so my circle is perfect. I did it. Now, before we start with this, I'm gonna tell you some facts that you need to know, and please write it down wherever. I guess on this blank part right here. So look, when y is equal to any number, like y equal 10, y equal 5, y equal, you're gonna have a horizontal line. Okay, horizontal line, HL. When you have the equation x equal to any number, you are going to have a vertical line, okay? Vertical line. Now, those of you who were with me, and you already took class with me, you already know this. But those of you who haven't, then just right now, for your own sake, just remember this. It doesn't make any sense to you because y is the vertical axis, but still, no, just memorize this. Y equal to a number is going to be a horizontal line, and x equal to a number is going to be a vertical line. That's all you need to know. And if you write it on your handout, then it's going to be fine. All right, let's do this. So it says points that are 2 units from the line y equal 3. Y is a horizontal line, so y equal 3 is going to be right here. Got it? That is your horizontal line. Becker, you didn't dash it. I didn't dash it because I'm not supposed to. This is not the locus. The locus is going to be all the points that are 2 units away from this line. Get it? Oh, you're nice. Okay, so what's 2 units from that line? Sure. What is the locus of points equidistant to a single line? A pair of parallel lines. So that's exactly what I'm gonna do. That one, and then this one right here. Hopefully you can see it. All right then. Now, label with an X all the points that satisfy? Sure. Locus with the circle, pungum. Locus with the circle, pungun. Locus with the circle, pungun. Becker, you forgot about these 2 points. No, remember, this line is not part of your loci. Okay, this line is actually one of the original lines. That line needs to be there in order for me to, determine the loci. Okay, so good then. All right, let's move on. So let's see. On the grid below, graph the points that are equidistant from both the x and the y axis and the points that are 5 units from the origin. So guess what? Equidistant from both the x and the y axis. The x and the y axis are nothing more than a pair of parallel of intersecting lines. And we know that the locus of points equidistant to a pair of intersecting lines is nothing more than another pair of intersecting lines. In other words, the angle bisector of each of these. So that's exactly what I'm going to do. So the angle bisector, since this is already broken down into units, is going to be an equation of y equal to x. In other words, when x is 0, y is 0. When x is 1, y is 1. In other words, the slope is 1. Okay, so 1 up, 1 to the right, 1 up, 1 to the right, so on and so forth. It's gonna be something like that, right? Okay. Got it. Okay. And guess what? The same thing is gonna go for the other line. So it's gonna be 1 here. Okay. So let's see. Oh my God, forgive me if I didn't show you what I was doing. So another line right here. okay? Que bruto! It had to be a dashed line. Oh my God. Okay. So Becker, relax. I'll make a dash. Watch this. I'm nice. Oh, yeah. Waste the eraser like it doesn't cost money. Okay, so you got this right here, this right here, this right here. So you got your pair of intersecting lines. Slope of 1/1 over here and a slope of -1/1 over here. And we're good, okay? You should know what I'm talking about. Now, guess what? It's up to you. I'm gonna give you 1 minute to do this. Now you need to sketch the points that are 5 units from the origin. This is the origin, and you should know what 5 units should look like, okay? Optional, scrap. Why do I give you this scrap? So you could do this problem. How many points are both 4 units from the origin? Okay, we already know what this looks like. And also 2 units from the line y = 4. Well, I told you already what the lines equal to numbers are. So you should be able to do this. You could use this grid. And also, I want you to do this problem. It says in a coordinate plane, how many points are 5 units from the origin? You already know what that means. And 2 units from the x-axis, all right? So just make sure you know how to do that. All right. Summary should be easy. Set of points that satisfies one or more conditions. All right, let me see. Yes, we're done. No, we're not. I still have to show you the... Okay, I'm gonna be nice because it's the first few classes. So, all right, quiz number 20. Solve graphically and algebraically. What is the solution to the following system of equations? All right, then, to solve a system of equations, make sure that one line goes into the other, and one of them must be solved for y or for x. It doesn't matter. Since you are also gonna graph it, then guess what? You need to have both equations solved for y. Now, the easiest thing to do is just to use the calculator, but unfortunately, not. I don't want you to be doing that. So let's see. Let's do it algebraically first. So y is equal to x plus 2. So I'm gonna put this into y, but not this one, but this one. All right? Make sense? Sure. All right. So my new equation is gonna look like x plus 2 equals, okay, x plus 2 because y is x plus 2 equals, and then x squared minus 4x plus 6. We know this is a quadratic equation, so it must be equal to, look at the wall, it should be equal to 0. So I am going to make this side equal to 0. How? By subtracting x and by subtracting 2. So if I do that, this becomes 0. Now, what I do to one side, I gotta do to the other. So if I subtracted x and I subtracted 2, then I gotta do the same thing over here. All right? Now, let me add the like terms. So x squared, now negative 4x and negative x makes negative 5x. Okay. 6 minus 2 is 4, so that's plus 4. Good. Now this equation is factorable, so I'm gonna factor. Okay? So when I factor, factors of x squared are factors of 4, but I need a negative 5, sure. Negative 4 and negative 1. Now why? Because when I do the smiley face, okay, I'm gonna do my how should I do my smiley face? You know what? The smiley face like this, okay? Yeah, the extremes are gonna go in the bottom, and I'm gonna do like the little ones like that. That's gonna be my smiley face, although it doesn't look like a smiley face, but pretend it's a smiley face. Okay then, so negative 1x, negative 4x, that's negative 5x, perfect. So now, now when I solve for 0, I need each of the factors to look like 0. So what number minus 4 is 0? Positive 4. What number minus 1 is 0? Positive 1. Okay, 1 minus 1 is 0. So my solutions are going to intersect at when x is 4 and when x is 1. But this is not complete. I need my y values. Sure, take each of the x values and plug it into one of the original equations. This is the easiest one, so that's the one I'm going to use. So y equals to x plus 2. All right. So now I'm going to use when x is 4. So I have y equal 4 plus 2, which equals 6. So when I use 4, y is 6. So my solution is going to be 4, 6. Okay, now let's go into the other solution. I'm still going to use the same equation, y equals x plus 2. But now I'm going to use the value that I got for x, which is 1. So y equals to 1 plus 2, which is basically 3. So when x is 1, y is 3. What the hell does that mean? These are the points where when I graph these lines, I get the lines intersecting. Really? All right, let's try it. So let me graph y equal x plus 2 first. Y equal x plus 2. What is the y-intercept right now? 2. So I will start at 2, okay? So my y-intercept is 2, so I start at 2. Now, for 1 point, what is the slope of this line right here? 1, right? Okay, so the slope is 1, positive 1, so 1 over 1. So I'm going to go 1 up, 1 to the right. 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 Or I can go 1 down, 1 to the left. 1 down, 1 to the left. 1 down, 1 to the left. That's it. I grab the line. I grab the line. Becker, show me how I grab the line. Sure. So the line looks like this. Perfecto. You are the best, Becker. I know. Okay. So that was the easy part. Now let's graph the parabola. What the hell? The what? The parabola, you know, the quadratic equation. This is the shape of the quadratic equation. Oh, okay. So let's see now. What do I do? Well, I would advise you to create a table of values. But the first thing I advise you is to find the axis of symmetry of the parabola. And how do I do that? Easy. The equation for the axis of symmetry, okay, is x equal to negative b over 2a. So this is the equation, okay? Okay? So let us find the equation of the axis of symmetry. Negative b over 2a. First of all, I need to find a and I need to find b. A is the numerical value of x squared, which is 1. B is the numerical value of the linear term. So in this case, b is negative 4. And of course, I don't need b. I need negative b. So that will be positive 4 because negative b is the opposite of b. And if b is negative 4, then negative b is positive 4. Okay, I get it. So let's find the axis of symmetry. So negative b over 2a. That means 4 over 2 times a. What is a? 1. So 2 times 1 is 2. So the axis of symmetry is 2, meaning x equal 2. But then again, I need to find the y value to find the vertex. But this is good because now I know how to create my table. Okay? This is good because now I know where the middle of my table is. The x value is going to go around here. Okay? That's the middle. So I know now which values to give. For example, up here I'm going to give 1 and 0. Down here I'm going to give 3, 4, and 5. All right. So let's figure out what these values are by hand. Let's start with... Wait, hold on a second. I already have 2 values. Look. The equations intersect at 4, 6. So when my value here is 4, I know that this is going to be 6. They also intersect at 1, 3. So I know that on the table, when I have 1, this is going to be 3. Nice. Okay. Now, 2 becomes the turning point. So I'm going to figure out what 2 is, okay, the y value for when x is 2. So let's see now. 2 squared is 4, minus 4 times 2, which is 8, so 4 minus 8 is negative 4. Negative 4 plus 6 is 2. Oh, so this is 2 comma 2. Nice. Guess what? Since this is the turning point, then 3 is gonna be 3 comma 3. Okay, the values repeat. Since 4 is 4 comma 6, then I know that 0 is gonna be 0 comma 6, because in a parabola the values repeat. Okay, so that's what I'm gonna graph. Okay, so 0 comma 6, that's what I'm gonna graph first. All right, 0 comma 6 right here. Then what is the other value we have? 1 comma 3. 1 comma 3. Oh, look, it does intersect. The next one is going to be 2 comma 2. The next one is going to be 3 comma 3. You see how they start repeating? So you already know that the next value is going to be 4 comma 6. Okay? And now just draw your parabola. Your parabola should look like this. Okay? And now on the other side. I'm taking too long, I'm sorry. All right, so basically this is what you get, and make sure that you label the points of intersection, like this is 1 comma 3, and that this is 4 comma 6. You need to do this forever and ever and ever. And that, my friends, is your first quiz for this trimester, or your quiz number 20, or your quiz on loci, whatever you want to call it. All right, good. All right, so we're done. And now next time we're gonna go on to the next lesson. Okay, bye.